In this lesson, we will focus our attention on understanding IPv6, which stands for the Internet Protocol version 6. IPv6 represents the most recent version of the IP protocol building upon IPv4. It provides for an avenue for the identification and location of specific devices on networks and is able to route traffic through the internet. IPv6 was originally introduced by the Internet Engineering Task Force and was first commissioned in 1998 as the next standard for internet traffic. So it is based upon the 32-bit components of IPv4 and was built to provide for larger addresses. Some of the goals included having more efficient processed headers and header changers that can be implemented to facilitate quality of service. And so there is still both IPv4 and IPv6 are being utilized. And so there are some considerations to take into place for why it's been adopted so slowly in a widespread manner. And so the major differences between IPv4 and IPv6 is we have a fixed length 40-byte header, and it allows for additional options after the header. No fragmentation is allowed. No broadcasts, only multicasts. The addresses are 128 bits, with the network part always the first 64 bits of the address. With IPv6, you have 1.8 times 10 to the 19th subnets and 1.8 10 to the 19th hosts on each subnet. It makes use of neighbor discovery protocols to replace ARP. Also with IPv6, NAT is discouraged, but local addresses are still widely available. And every interface must have a linked local address. Additionally, it is considered to be impractical to scan a subnet for available hosts as well. And so in breaking down the IPv6 address space, you'll want to consider that you have 128 bits that are utilized. The first 64 bits represent the network, and the remaining 64 bits are used for identifying the hosts. So this includes 8 16-bit hex numbers that are separated by colons to represent the address. And so when you encounter a dual colon, that means you fill in with the zeros, but only one is allowed. And so this means that we could have a IPv6 address that is written using the 8 16-bit hex numbers, or it can also be further written and simplified in the following other forms as well. So our first bits will be represented for the network components, and then the last will represent the interface identifier or the host. And so if we wanted to consider how this is encompassed on campus, we would have appropriate bits that are represented to understand the major business units that is utilized. We can have it to represent the existing class, And X and Y represent the last two octets and are similar to our IPv4 subnet addressing scheme. So let's also now take a look at the data link layer, and specifically protocols used to operate the Ethernet. And so let's talk a little bit about the Ethernet and the considerations that we want to consider. The Ethernet is you want to consider that the Ethernet is a particular type of data link network, and it was designed for relatively small areas like buildings, and so comes from the term LAN for local area network. Ethernet also has its very own standard. It uses the IEEE 802.3 standard, and it has evolved a great deal since the 80s. To talk about some of the terminology that is associated with the Ethernet, let's consider we have the collision domain, and the collision domain represents all of the network interface cards that share a physical Ethernet, but only one can transmit at a time. We have a broadcast domain where all of the network interface cards that can hear an Ethernet broadcast frame occur. Repeater or hub represents layer 1 replication and amplification of bits. Bridges or switches are part of the layer 2 retransmission of the Ethernet frames. And the router represents the layer 3 forwarding packets based on layer 3 IP routing tables. Hosts include the computer or one or more network interface cards that forge traffic using multiple network interface cards. So this can also be analogous to a router. And so when you consider Ethernet addressing, you want to consider that every Ethernet device gets its own unique MAC address. And so the MAC address is going to represent 6 bytes or 48 bits. 3 bytes are representing the OUI, and 3 bytes are representing the NIC or NIC specific. So for example, Apple device could be represented in the following format, while an Oracle device would be represented in the defined format using dashes. And so you can use Wireshark to identify your address as well. So the format for Ethernet frames. So to send the frame, you have to wait until no one's using the cable. You assert the carrier signal on the cable. You broadcast the frame to all stations on the cable. And if you detect a collision while transmitting, you stop and requeue the frame for retransmission. If you hear a frame on the cable, you accept it if the destination MAC belongs to the network. You drop it if you see a collision during its receipt, or if its CRC doesn't match. So this is where CSMA CD comes from. So we can consider that only one station can send at a time, but where are the IP addresses? Well, first, let's consider a little bit of history with regards to Ethernet topology. Initially, we were able to start with a few hosts that are connected via a AUI cable. These also include a transceiver and coaxial cable, as well as a terminator. These are the kind of the foundational building blocks that were used to provide for an Ethernet connection. This allowed for us to enable multi-port connections to occur and introduce other physical components that allow for more expansive topologies. And so this introduced Cat3 and Cat5 twisted pair cables that could be utilized. This allowed for the establishment of collision domains. Bridges were able to be incorporated as well. This allowed for a broadcast domain that could be utilized. Which enabled for multiple networks to be established based off of market needs, and in large part through to the inclusion of thin coaxial cables that could be utilized to provide for more advanced topologies. Including more detailed networks, we were able to utilize parallel ports that allow for multiple Ethernet adapters to be used. This enabled Ethernet ports to establish more workstations that could be used and connected via switches and base stations. And so how does the Ethernet bridging algorithm operates? Specifically, when a frame enters the bridge, the destination MAC address is, if the destination MAC address is in the bridge table, we send the frame out to the port listed in the bridge table entry. If not, we flood the frame out all ports except for the ingress port. We'll then want to put the source MAC address in the bridge table if necessary, along with the frame ingress port, as well as, and mark that entry as recently used. We'll remove any entries that haven't been used in the bridge table as necessary. So this has provided an avenue of how Ethernets are connected and how the bridging algorithm works, but something else is missing. Now we can have more than one message in transit at a time. But we've only talked about MAC addresses. So where are the IP addresses at in this in Ethernet transmission? In order to accomplish this, we consider layer 3 packets. And so we have to consider the IP addresses appear in the internet frame payload, not in the header. But Ethernet hardware only examines the MAC address in the Ethernet frame. So how exactly can we connect these two layers? And so in this, we incorporate the address resolution protocol. We use it with the Ethernet to discover IP addresses. And so how is this done? We make use of the IP stack needs to send IP address A, but doesn't know what destination MAC address to use. We broadcast an ARP request message that says, who has IP address A? We'll then need to wait on a unicast ARP response, and then that says, I have IP address A. We then store the response in a local ARP table and discard entries when they become stale. We can then use the corresponding entry in the table to set the destination MAC address. Using this, we're able to use our link layer addresses to determine the appropriately IP address that could be utilized. This enables us to determine the IP address, the mask, and based on to the physical address as well. Now we can talk about virtual local area networks. Specifically, what exactly is a VLAN? A VLAN is going to represent a group of hosts that can communicate as if they were attached to the same broadcast domain. And this can be regardless of the physical location. You want to keep in mind that a VLAN has the same attributes as a physical local area network, but it allows for hosts to be grouped together even if they are not connected to the same network switch. Network reconfiguration can be done through software instead of physically relocating devices and wires, which is why we call it a virtual local area network. And so, generally speaking, we would make use of, in a typical setting, we would have just a router with switches and switches connecting multiple devices. But if we wanted to incorporate a virtual local area network, we would need an appropriate switch to be utilized. And each logical VLAN that we want is a separate physical bridge. So we could have red representing the College of Engineering, black representing the College of Computing, and green representing a classroom network. And we can have switches on each floor, and each logical VLAN is like a separate physical bridge, and VLANs can span across multiple switches. And so let's explore how that is done. Well, if you remember, we have the 802.1 Q tag in the Ethernet frame. We fill that with a VLAN number that can range from 1 to 4095. Essentially, we'll tag the frame. With each edge port, we label it with the VLAN number, and we include appropriate switches that tag each frame as it comes in. We segregate traffic carrying those identical VLAN tags, and we output the tag traffic to edge ports carrying the same VLAN tag. But we still need to address how these switches communicate. And so communication occurs using trunking. And so what a VLAN trunk is a mechanism that can be used that we can provide network access to multiple clients that share appropriate physical resources. So trunks act like an interswitch between that preserve the VLAN tags on links between switches. So trunks can be configured to carry one, several, or all VLANs from one switch to another. And each VLAN is a trunk, uses up switch resources, and so it allows for the trunks to be configured to only carry necessary VLANs. And so in this example, using trunks, we are able to denote that all the green ports appear in one broadcast domain, the red ports appear on a different broadcast domain, and the black ports on a third broadcast domain. VLAN tags are carried by ports, and trunks are all configurable in software. Okay, so now let's look at our last layer in the OSI model, the physical layer. And the physical layer is basically going to represent the means and mechanisms that we have for transmitting our raw bits over our data link components. When we think about Ethernet physical media standards, we have twisted pair copper as well as fiber optic, and each one has an appropriate base that allows for appropriate transmission of data at a wider or faster speed. And when you compare, twisted pair is most often used with telephone communication as well as some Ethernet networks, while fiber optic is used as a type of Ethernet cable that consists of multiple optic fibers to transmit data at a high speed. This basically means it's able to transmit data at pulses of light through tiny tubes of glass. And essentially, you can consider that optical fiber transmission is going to be about 26,000 times faster than using twisted pair. The cables make use of Manchester encoding, and this allows for a scheme that guarantees at least one voltage transition will occur during each clock cycle. So it's representing a self-clocking signal, so there isn't a DC component involved. And so let's consider the components that we have in a home router, where we might have a firewall, a wide area network, those components connected to a 2-port router, and we can have various switches that are also available to connect, as well as maybe a wireless access point to guarantee Wi-Fi connectivity. With all of these components involved, let's specify specific performance metrics. And so when we talk about performance, we're talking about the transmission time or the end-to-end latency that is that our modem will transmit. And then we're also talking about message throughput. And so we want to consider S being the processing overhead at the sender, R being the processing overhead at the receiver. T sub F is going to represent the flight time, and T sub W is going to represent our wire delay. And so our transmission time is going to be the processing overhead at the sender, the wire delay, plus the flight time, plus processing overhead at the receiver. And so what determines our wire delay? How long it takes to put the message on the network. T sub W is going to equal the message size divided by the network bandwidth. So example, 21 megabytes at 56 kilobytes per second. 21 times 2 to the 20 times 8 divided by 56,000 is going to give you 3,146 seconds for our wire delay. What determines our flight time? It is basically going to be the speed of light in the transmission medium. And so how far is it from P1 to P2? The queuing delay is an additional term as well. So what determines processing overhead at sender and processing overhead at receiver? It'll be based off of the OS implementation stack. So let's consider an example. We have 100 milliseconds latency with a wire delay of 0.5 milliseconds and a wire delay acknowledgement close to 0. Receiver and sender overhead is close to 0. We have 10 packets and a window size of 5. So if we're transmitting 5 packets, we have a 0.5 millisecond delay. And then we consider 100 plus 100 milliseconds. We get to our acknowledgement. Then packet 5 is transmitted. We have our acknowledgements that come in. And then this is going to be 4 times 0.05. So our end-to-end latency for packet 0 is going to be 0 plus 0.05 plus 100 plus 0, which is going to give us 100.5 milliseconds. Our end-to-end latency for our acknowledgement is going to be 0 plus 0 plus 100 plus 0, so 100 milliseconds. So our total transmission time, if we multiply that by 5 and sum, so we have 0.5 plus 200 plus 0.5 plus 200 plus 4 times 0.5. So we have each time that is based off of each packet that is being transmitted. And so in the expression S plus TW plus T at sub F plus R, what is our appropriate value that we want to consider for T of W? Is it equal to window size? Is it equal to message size over network bandwidth? Is it going to be distance between endpoints over 0.5C? Is it going to be sender overhead plus receiver overhead? And as we discussed earlier, this is going to be equal to our message size over our network bandwidth. And so these are a couple of main points related to IPv6 as well as Ethernet technology and associated performance metrics.